right? So our today's study will be mathematical expectation of a function of a random variable for continuous case, right? So here consider let g of x is any function, right? So let uh, g of xy say let f of xy is our joint density function is our joint density function or joint probability density function, joint probability density function, and g of xy is any other function, any g of xy is any other function, right? So then the expectation of bivariate case of such functions, right? So the expectation of, I mean expected value of this g of xy, so that is expected value of g of xy is given by, so expected value of g of xy is given by double integration. So one integration minus infinity to infinity, one more is also same, minus infinity to infinity, g of xy into f of xy into dx dy, right? So provided all the double integration exists, right? It means that the double integration should be exist here, right? So this is what the formula to find out the expectation of bivariate case, right? Say x and y are any two random variables with the probability density function f of xy and g of xy is any other function, then the expected value of g of xy is given by this formula, that is integration minus infinity to infinity. This integration because of one variable, that is x, and one more integration because of another variable y. So double integration minus infinity to infinity g of xy into f of xy dx dy, right? So this is what the formula to find out the expectation of g of xy when x and y are continuous case, right? So now we go for examples here. Okay. Examples. Suppose xy, I mean x comma y is a bivariate, is a bivariate random variables. Suppose x comma y is a bivariate random variables with PDF, with PDF f of x comma y equal to x into y. So range of x is 0 to 1 and range of y is also mentioned, that is also 0 to 1. Then find first one expected value of x plus y, second one expected value of xy, right? So here we need to find expected value of x plus y and expected value of xy, right? So here what is the given? They given, what are they given? They given that the joint probability density function is, the joint probability function is f of x comma y, right? So what are they given? Where f of x comma y is equal to x into y, right? So they mention the limits also 0 to 1 and 0 to 1 for y also. The first one. So what I required expected value of xy. So here g of xy is nothing but x plus y. So double integration minus infinity to infinity, minus infinity to infinity, right? So g of x comma y, f of x comma y, dx dy. So this is equal to integration as it is, but here minus infinity is lower limit of x. So lower limit of x is 0 to 1, and one more is lower limit of y to the upper limit of y, that is 0 to 1. So instead of g of x, what do we have? We have x plus y into, instead of f of xy, what we have? F of xy is x into y, xy. So dx dy, right? So now we'll solve the integration step by step. So 0 to 1. So first I will multiply this xy into inside, right? So first I will multiply this xy into x, right? Later we go for xy multiplication for y, right? So here first 0 to 1, 0 to 1, then first x into xy, right? So x into xy plus xy into, so I mean y into xy, so dx dy. So now equal to integration 0 to 1. So here what we'll have? X is, just a wait, integration 0 to 1, one more integration 0 to 1. Now what we have here? X square y plus x y square dx dy, right? So first I will integrate whenever we have double integrations or any number of triple or any number of integration. So first we'll do integration variable wise. So 0 to 1. So first I will integrate with respect to dx, then I go for with respect to dy. So 0 to 1, x square y plus y, sorry, y, x into y square. This is integration with respect to dx and dy as it is, right? From here to here, this is our function. So this is with respect to dx. Now equal to 0 to 1 as it is, open bracket. So what we have here? Integration of x square y with respect to dx, right? So integration 0 to 1 x square y, integration 0 to 1 x square y dx plus integration 0 to 1 xy square dx, then here dy. So 0 to 1 will integrate with respect to x, and y will be treated as a constant. So I will take outside, then x cube by 3, 0 to 1. So square bracket as it is, y will be constant. So I will take outside. So y into, we know that integration of x power n is x power n plus 1 divided by n plus 1. So that is x square will be x cube divided by cube, right? Plus. So here y square will be constant because we are integrating with the variable x. So y square will be constant. Now integration of x is x square by 2 over the limits 0 to 1 dy. Integration 0 to 1. So this is nothing but y by 3 into 1 cube minus 0 cube plus y square by 2, 1 square minus 0 square. This is what dy as it is. Integration 0 to 1. So now what we have? Y by 3. Y by 3 into 1, that is will be y by 3. Plus y square by 2. Right? So for this we have dy. Now integrate again. So integration 0 to 1 y by 3 dy plus integration 0 to 1 y square by 2 dy. So 1 by 3 I will take outside because it is constant. Integration 0 to 1 y dy plus 1 by 2 integration 0 to 1 y square dy. Same 1 by 3, this will be y square by 2, 0 to 1. 1 by 2 y cube by 3, 0 to 1. This is nothing but 1 by 6, 1 square minus 0 square, plus here also 1 by 6, here also 1 by 6, because 1 by 2 into 1 by 3, it is 1 by 6, 1 cube minus 0 cube. So this is 1 by 6 into 1, that will be 1 by 6. Here also 1 by 6. So 1 by 6, 1 by 6, the answer will be 2 by 6, the answer will be 1 by 3, right? So this is what the first sub answer. Next, we need to find second sub answer. What we need to find? We need to find expected value of xy. So expected value of xy is nothing but integration minus infinity to infinity g of xy f of x comma y dx dy. So here in this equation 0 to 1, 0 to 1, this will be xy, then f of xy will be, that is also xy dx dy. See, I told you to join at what time and what time you are joining. Please. So now expected value of xy equal to double integration 0 to 1. So here xy is there. So that will be x square y square dx dy. So this will be integration 0 to 1, integration 0 to 1 x square y square dx, then dy. So expected value of xy equal to integration 0 to 1. So here y will be treated as a constant, so it will be outside. Here it means that y square, then integration of x square is x cube by 3, 0 to 1 dy as it is. This is equal to integration 0 to 1 y square by 3 into 1 cube minus 0 cube dy. This is equal to 0 to 1 y2 by 3 dy. So this is 1 by 3 I will take outside. Next, integration 0 to 1 y square dy. So 1 by 3 y cube by 3, 0 to 1. So this is 1 by 9 y cube 0 to 1. So now 1 by 9 into 1 cube minus 0 cube. So expected value of xy will be 1 by 9 into 1 minus 0, that will be 1 by 9. Right? So in this way, we need to find out the integration. So whenever we have that bivariate concepts, right? So I hope it's clear. So next we have theorems. So how we prove that addition theorem of expectation for discrete case. Now we are going to solve the addition theorem of expectation for continuous case. Right? So theorem. So this is known as addition theorem. addition theorem of expectation in continuous case, right? So addition theorem of expectation in continuous case. So first we go for the statement. First we go for the statement, right? So if xy is a bivariate random variable, if xy is a continuous bivariate random variables, with joint PDF, f of xy, then expected value of x plus y is equal to expected value of x plus expected value of y. So we need to prove this theorem, and this theorem is also called as addition theorem of expectation for continuous case. So proof, right? So by the definition, what we have left side, we have that expected value of x plus y. So by the definition, it will be integration minus infinity to infinity over the x, integration minus infinity to infinity over the y. So instead of g of xy, what we have f of xy, sorry, x plus y into f of xy dx dy. Why we consider? Because of definition, right? So by the definition. Now expected value of x plus y equal to, so double integration as it is, minus infinity to infinity, minus infinity to infinity. Now we have here x plus y. So we'll multiply this f of x for the first x, then plus for y, right? So it means x f of xy, and here we have dx dy plus double integration minus infinity to infinity y f of xy dx dy. It means that here we have bond, that is x plus y, we break like this, right? So now again the procedure will be same here. So integration minus infinity to infinity, so x integration minus infinity to infinity f of xy dy into dx, right? It means that what, sorry, here we will take this x outside, right? It means that we are taking first with respect to dy. So this is dy like this, plus integration minus infinity to infinity. So here I will take y outside, y. So integration minus infinity to infinity f of x comma y dx dy will take outside. So now which is equal to integration minus infinity to infinity x into, right? So this is nothing but the whatever we have, this quantity is nothing but marginal uh, distribution or marginal probability density function of x, right? So this is nothing but marginal distribution of x, right? So I told you whenever we are opposite we take, so this is nothing but marginal distribution of y, right? Clear. So here marginal is nothing but what? This is nothing but f of x dx, right? Plus minus infinity to infinity y, marginal means f of y dy as it is. So dx as it is, dy as it is. This is nothing but marginal distribution. This is denoted to f of y. So here, this is nothing but our expected value of x definition plus as it is. This is nothing but our expected y definition. So here left side what we have? Left side we have expected value of x plus y, which is equal to expected value of x plus expected value of y, right? So this is nothing but the very simple proof of addition theorem of expectation in case of continuous case, right? So regarding this, we have some remarks here. So the first remark, if a equal to 1 and b equal to -1, then expected value of ax plus by is equal to what? A into expected value of x, b into expected value of y. By our univariate or one-dimensional expectation, we know this, right? So now put a equal to 1 and b equal to -1. That is nothing but a equal to x minus y. A is 1, so 1 into x, minus 1 into y minus y. So this will be a into expected value of x, that is expected value of x, minus 1 into expected value of y, that is nothing but expected value of y, right? So it means that this is also true, right? So this is also true. Then second condition, in generally, right? So in generally, expected value of x1 plus x2 plus x3 and so on up to xn is equal to sum of their individual expectations. So this is nothing but expected value of x1 plus expected value of x2 plus expected value of x3 plus and so on up to plus expected value of xn. So the second remark is also called as the generalization of addition theorem of expectation, right? So this is what the concept of addition theorem of the expectation. Now we go for multiplication theorem of expectation. We have one more theorem. This is called as multiplication theorem of expectation, right? So here we go for the statement. Same, if xy is a bivariate continuous random variable, bivariate continuous random variables with joint PDF, means joint probability density function f of xy and x and y are independently distributed, means those are independently distributed then expected value of x into y is given by expected value of x into expected value of y. So this is what the statement of multiplication theorem of the expectation. So now we are going to prove this theorem. Proof. Same consider by the definition, that is expected value of xy is equal to double integration minus infinity to right. So first here, right? So this is called multiplication theorem of expectation. The statement will be expected value of x, sorry, statement if xy is a bivariate continuous random variable with the joint density function, that is PDF, f of xy, and x and y are independently distributed, then this will be exist. That is expected value of xy into expected value of x, sorry, expected value of xy equal to expected value of x into, means product, expected value of y. So here we'll consider the definition, double integration xy f of xy dx and dy. And then I told you already, if x and y are independent, then this will be exist. That is nothing but f of xy equal to f of x into f of y. So this is an example. E power x plus y equal to e power x into e power y, and then we say uh, x and y are independent, right? So next here, consider f of x is a marginal distribution of x and f of y is a marginal distribution of y. Then expected value of xy, double integration xy f of xy dx dy. Same double integration xy f of x into f of y. Why? Because this is independent. Where we are saying x and y are independent, so we can split like this, right? So we can split f of xy equal to f of x into f of y dx dy. Now I will take one integration here, x f of x dx. So x f of x dx into another integration. Nothing will be changed from here to here, right? So both are equal. So this is nothing but sorry, here integration minus infinity y into f of y dy. So this is nothing but our expected value of x definition. This is nothing but expected y value or expected value of y definition. So here this implies that expected value of xy is equal to expected value of x into expected value of y, if and only if they are independent. Next, we have a generalization of that theorem. That is, if x1, x2, x3, so on up to xn are independent random variables, then expected value of x1, expected value of x1, x2, x3, so on up to into xn is equal to expected value of x1 into expected value of x2 into expected value of x3 into and so on up to into expected value of xn. So this is called as generalization theorem of multiplication of the expectation. After that, we have one example, that is let x and y be continuous random variables with the joint density function f of xy equal to 2. If they given the range here 0 less than y less than 1 minus x, then one more limit of the x, that is range of the x, that is 0 less than x less than 1, then find then find expected value of xy. So here we got, that is answer is 1 by 12. So here f of xy equal to double integration xy into f of xy dx dy. So double integration f of xy is 2 they given. So we'll take 2 here, xy dx dy. So here first I will take here outside dx. Y means the x, so x is the only random variable. Here it has independent limits, but here y has dependent. So that's why we'll take y inside. So 0 to 1 integration 0 to 1 integration 0 to y. So that will be 0 to 1 minus x. 2 times of xy dy dx. Now integration 0 to 1, 2x is a constant, will take outside the integration sign, then integration 0 to 1 minus x y dy dx. So integration 0 to 1, 2x, so integration of y will be y square by 2, 0 to 1 minus x dx. So these two get cancelled. So now what we have, x as it is. Then y square means 1 minus x whole square minus 0 square dx. So x 1 minus x square dx. So here we split by a minus b whole square formula, that is a square means 1 square plus b square means x square minus 2ab means minus 2 times of 1 time of x, that is 2x dx. So we'll multiply this x inside. So x square, sorry, x into 1 square, x into x square, that is x cube minus is same as it is 2 times of x square dx. Then we'll multiply, sorry, we will take integration of these individual, that is integration 0 to 1 x dx plus integration 0 to 1 x cube dx minus 2 as it is minus 2 integration 0 to 1 x square dx. So here x by 2 0 to 1 plus x is 4 by 4 0 to 1 minus 2x cube by 3 0 to 1. When we insert upper limit minus lower limit, here we'll get 1 by 2 plus as it is 1 by 4 minus 2 by 3. After some simplification, we will get 1 by 2. Clear? So here, whenever due to that network loss, that video and this video will be merged, and we'll share a common link for it.